It's my real pleasure to stand here and present you perhaps 1-hour lecture. This is my very first visit to Denmark, but I hope it is not the only one. Anyway, what I would like to do today is to discuss the magical power of transition metals, but more specifically D-block transition metals. And you may have forgotten what D-block transition metals are. I'm sure there's at least one. You will, don't worry. And I am presenting this because this area represents my lifelong research, projects. But more than that, I truly believe that it is a whole bunch. There are 23 of them that we can use, D-block transition metals, that will, I believe, save or promote our society to higher prosperity and help develop prosperous and a sustainable society. So I have a fairly large mission. Anyway, so sometimes I combine these two, and this is meant to be the past and then present, half of the present. The other half is a half of the present and the future, maybe. But today, when I put in some piece of information, including high school students attending and so on, I decided to concentrate on this one. Okay. And let's see. So this is... Well, as a synthetic organic chemist, about 50-some years ago, when I went to University of Pennsylvania as a graduate student, I thought, as synthetic organic chemist, our main goal is to be able to synthesize all kinds, not just this kind or that kind or that kind, all kinds of organic compounds preferably in high yields, Y, and efficiently, E, and then selectively, S. Y-E-S. Yes. Of course, I got this from Barack Obama. Then I thought maybe a couple of others. We should synthesize them economically. E. And then safely. S. E-S. I have been looking for the second Y. If you can help me with this, I would appreciate. But anyway, for the time being, I settle with yes, yes, or yes, Y-E-S squared. That is my definition of green chemistry. If you have any objection to what I'm saying here, please let me know. And next question is, how to achieve this goal? Well, that's the kind of thing that I started worrying about as a graduate student in about 1961 or 62. And one of my puzzles was, why do organic chemists try to synthesize organic compounds, dealing mostly with so-called 10 or dozen organic elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and some halogen. Maybe sprinkle in some few metals, like a magnesium in Grignard chemistry, or alkali metals and so on. That's about it, maybe up to 20. Then if you look at the periodic table, then you see 112 or so. The number is slowly increasing, I understand, but even when you forget about some, then you have 100 plus. Then I realized that we don't get to use not all of them, but we can still consider all usable elements. And in my mind, there are about 70 of them. When we avoid the radioactive one, there are a fair number of them, all above 84, polonium, and then the technetium. And essentially totally, not quite completely, but very inert gases, 5 of them, and inherently toxic elements. Okay, maybe I have like that. This is anatomy of the periodic table in my way. So these green ones, there are 11 of them shown. I call them organic elements. We need them. We need them in stoichiometric quantities. Then, of course, there is this, by excluding inert gas, and then any element after polonium, including this one, and then all these, except for these. Then and then I was telling you that there are some, up to 10 maybe, they seem to be intrinsically toxic. In other words, no matter how you use them, then you end up getting toxic material. Beryllium, cadmium. Japanese know very well this hazard of cadmium. Japanese also know very well the hazardous nature, toxic nature of mercury. And thallium, lead. And I tend to think that the tin is also a toxic element which we should try to avoid, along with this arsenic. By the time you avoid all these, then you are left with about 70 of them. And as I said, in addition to about 10 or so organic metals, 11 shown here. So we are asked to avoid, we should try to avoid these. I just told you. But we still get to use 21 main group metals, alkali metals, magnesium, alkaline earth, and then zinc. I have become very much fond of this zinc, as you will see. And then all these group 3, group 4. Some of these are also appear to be okay. 20 or so main group metals. But what I have been emphasizing is this golden 23 golden ones. It's not yellow, it's golden. Okay? Let me emphasize. Those are called the D-block transition metals. 24, 3 times 8, minus 1, 23. These are the ones in the past, half a century ago, most of these golden ones were used mainly as materials, like a gold, silver, copper wire, copper kettle, or whatever, and iron and chromium and nickel, that's a stainless steel, and more precious metals like a platinum, iridium, and so on, and so on. Mostly as material, you get to see. But for the past maybe half a century, maybe quarter of a century, chemists have found that they are special class of elements as chemical species. Especially, they can serve as a catalyst without really fundamentally sacrificing them. In other words, they can come around and around and around. How many times? 10 times? Well, 10 times will qualify them as catalysts. But 100 times? 1,000 times? 10,000, 100,000, million. Million times? Yes. Or 10 million, 100 million, a billion? Yes. You know, catalysts fundamentally should never be consumed. Well, we all benefit from having some of the three of the most expensive one. I believe that's gold and platinum and iridium. Yeah, I may be partially wrong. We have them, each of us, at the dirtiest part of your car, right? Underneath your floor in a pollution control device box. You have these, some of the most precious, most expensive ones. But we can afford having them without even thinking about their value. And they're supposed to work for over 100,000 kilometers or even more. Have you ever replaced that dirty box? That's what you have here in there. So this is a small but very important part of their jobs in the 21st century. This is my message. And let me just go ahead and tell you. They are really special in this entire periodic table, 23 of them, excluding this technetium, which is artificial and radioactive. We don't want to use them in organic synthesis. And in my today's talk, I will emphasize two things, or maybe one thing more. That is that they are so useful, one, because they can provide simultaneously in a valence shell, the very important orbital, valence orbital, empty orbital. Empty orbital means there is no electron in there. That means it is electrophilic. It can bring in 1 or 2 electrons, right? So they can serve as Lewis acid. Actually, they can initiate various chemical reactions. And filled-nonbonding electrons, 2 electrons. If you recall Pauli exclusion principle, no? Please. Then each orbital can accommodate either 0 or 1 or 2 max. That's how he won his Nobel Prize way back somewhere. When? Okay, so these D-block transition metals can provide simultaneously empty orbital that can serve as electron sucking the Lewis acid this way. And then the filled-nonbonding orbital, 2 electrons, they can provide 2 electrons. That is a base. In other words, acid and the base together. Please remember this. If you don't understand any chemistry, just remember. Simultaneously. That's, to me, is one extremely important feature of all these D-block transition metals. Hardly anything else can copy that. Well, that's not quite true. We can even copy that feature with a carbon. How can carbon be like that? If you have learned about carbene, the carbene has 1 empty orbital and 1 filled-nonbonding orbital with 2 electrons. So carbene is a fantastic reactive chemical species. So in a way, these D-block transition metals can be carbenoidal, carbene-like. But they are much, much more useful than carbene. Virtually none of us has seen carbene. Carbene cannot sit around. D-block transition metals, gold, for instance, just take. Gold can stay forever in a shiny form. So they're thermally stable and yet they can do what I was just telling you. Very mysterious magical power, ability. Okay, so that's one thing. And if I give you the second one, you can leave this room. That's the only two messages that I'm giving you, maybe. Second magical property of these golden D-block transition metals. They can be, or the compounds containing them, in them, they can be oxidized. You know, oxidation and reduction is critically important chemical processes. And then reduced, oxidized, and reduced in one vessel under one set of reaction conditions. If you think of these two contradicting phenomena, to my knowledge, nothing else can do that well. Well, we know, some of you may be thinking, sulfide can be readily oxidized, and sulfide or sulfone, oxidized product, can be readily reduced. So oxidized and reduced. So what's wrong with sulfur? Well, so sulfur can be oxidized or readily oxidized or reduced, but not in one flask, or not in one vessel, not under one set of conditions. Okay? So you have to oxidize in one pot, then get the oxidized product, and then in another vessel, you can reduce it. But you have to do it here and there, not in one flask. But with the D-block transition metals, you can do both in one flask. Some palladium, for instance, species are getting oxidized here or here in one flask. At the same time, in the meantime, some other palladium-containing species are reduced back. If you think of the catalysis, you don't want to do catalysis in this flask, partially, and then go this one and this way, million times, go back and forth. No way. So you have to be able to ask your chemical species to get oxidized and reduced under one set of conditions in one vessel. Only then you can have redox catalytic processes. Those are some of the most important ones. So then you realize that for these two reasons, you have to ask these D-block transition metals to do the job, to build a sustainable society while benefiting from chemical processes. Okay, so I have presented the key message of today already. And if you recall my YES thing, there are some synthetic organic chemists who think that they can make anything. But then, when the molecular organic compounds get a little complex, then they need 20, 30, 40, 50 more steps. Then I want you to realize that at an average yield of 90%, which is very difficult to maintain actually in reality, if you go beyond the 30 step, then you get only a 1.1% or so of the total material that you put in. You make junk from the rest. So this, namely, 30-step long synthesis is, to me, just the max. This pertains to, of course, efficiency. If the average yield is 80%, most people are very happy with this 80% average yield. Then your synthesis has to be less than 15%. This below that, most of the material that you put in are going to be junk, waste. If it goes down to 70%, then it better be 10%, 10-step synthesis or 10-step or less. Okay, so we should keep that in mind. With all these things, keeping all these things in mind, I thought about how should we make all kinds of organic compounds. What would be the most generally applicable organic synthetic method? And I came to this Danish notion. That is a Lego game. You people, your country has created this Lego game. But I have one complaint to make officially. I ended up buying Lego game boxes, 3-4 times. And then I realized, then only did I realize, I cannot even make a benzene ring. Because it's 120-degree angle. It's either a straight or perpendicular. So I want to register my formal complaint. And hopefully our junior high and high school kids buy your Lego game, and then build up molecular models. Anyway, so my Lego game approach is shown here. Well, I think we can go back to this one. So here's the Lego game approach. So here's the compound, organic compounds you want to synthesize. And the most important, most prevalent operations that you want to have, you need to take care of, is this carbon. These two groups are carbon groups, R1 and R2. Formation of the carbon to carbon bond. So the most critical operation is the carbon to form carbon to carbon single bond. It's nice to be able to double bond and triple bond additionally, but most important is single bond to form this one. Now, how to do that? Well, there was one way, Grignard. So by having a magnesium here, or metal, other metal. Metal is positive element. Therefore, the carbon attached to metal will bear partial negative charge. So R2 is negative. And then if X is so-called heteroatoms like halogens and so on, then this is negatively polarized, so R1 is positively charged. So by mixing these two, Grignard reagent and R1, negative R2 and the positive R1, negative and positive, they attract and then form the bond. That's true. And by so doing, they can produce R1, R2, this one, straight from here. It sounds fundamentally reasonable, and it works. It works. And Grignard chemistry does work, but it's very, very limited. Its scope is very limited. Like this. Organic compounds, organic groups can be by and large classified into about 10 kinds of groups. Aryl, alkenyl, alkynyl, triple bonded one, and aryl, benzyl, propargyl, alkyl, acyl, and enolate. And likewise, organic halides can be similarly classified, like so. About 10 and about 10. Here, I'm showing 9 and 8, I think, 72. And if we can couple any of these 72 different kinds of compounds to form R1, R2, you would have a fantastic, probably the most widely applicable organic synthetic method. And of course, Grignard, who won the Nobel Prize 99 years ago, so next year in 2012, 2012, we should be celebrating the centennial of the Grignards winning the Nobel Prize. That was the first, and he won it together with Sabatier. He won for his catalytic hydrogenation. So his version was a D-block transition metal catalyzed hydrogenation. Grignard version was a magnesium promoted, mostly stoichiometric reaction. I don't know of any catalytic versions that he published. I may be wrong, but anyway, mostly stoichiometric. So those two are combined, and then they shared the prize 99 years ago. Anyway, so in this method, with magnesium, magnesium here, then when these halides, unsaturated ones, they do not, by and large, they do not react. There are some exceptions, but let's not worry about those. Even when these carbons are alkyl kind, or acyl, more reactive one, then reactions are very limited. When they work, reactions can be erratic, something that textbooks do not recommend you to use, by and large. So this was a situation when I thought of a Lego game approach in 1962. And today, I can show this. Maybe a little better than this, but at least this. So those three red columns, now mostly green. They work very well, as you will see. And with the enolets, we have a little subtle difficulties. And these are also green. This is green. And with alkyl halide, we still have a little difficulty. But number of top-notch chemists in the world, Bachwald and Greg Fool and some European chemists, they are working on this, Japanese one, Nakamura, and they are making progress. But progress, in my opinion, have been coming rather slowly. And there's smack in the middle, these kinds of reactions involving two of the aryl, benzyl, or propargyl. 3 times 3, 9 categories. These have been the troublemakers. And I have given up on them. I said, don't try these. Because, so from here, by linking these two, you get 1, 2, 3, 4, 5, 6, 1,5-diene. Very important. Terpenoids and other important compounds are included. 1,5-dienes can also be synthesized by HOMO aryl. It's a 1 carbon longer, and this one is 1 carbon shorter. In other words, point of carbon-carbon bond formation has been shifted by 1 carbon. By doing so, we can handle synthetic tasks. Not in exactly the same way, of course, but we get exactly the same product in a wonderful way, as I will show you. And let me see. So this, if you, if you just compare this and this, going from this, as of, let's say, 1970, and this one, as of 1980 or 90, some of my friends said, wow, that's a revolution. I said, no revolution in scientific development. maybe evolution took us 30, 40 years, a bunch of us. But it looks like this has been a pretty good advances. And now some of us are beginning to claim that this arguably is the carbon-carbon bond formation, or organic synthetic reactions of the widest scope, widest applicability, beginning to surpass the whole of Grignard chemistry, in my opinion. Anyway, so that's one story. Let me see. So let me make sure, yeah, we have gone through this. Okay. And now I want to tell you why. Well, of course, I already told you, two things. One is ability to provide empty orbital and then filled non-bonding orbital simultaneously. And then being able to go up and down the oxidation scale under one set of conditions in one vessel. So, well, first of all, why metals? Why metals are so useful? Well, if you mix alkanes and alkenes under mild condition, room temperature, usually nothing happens. Mixture is mixture, stays as a mixture. Okay, now, but if you somehow convert this one alkane into a carbocation, corresponding carbocation, all of a sudden this gets very, very reactive, and then reaction like this can be observed. So, organic chemists have taught organic chemistry in a wrong way, in my opinion. Traditionally, in organic chemistry, we have taught students, think of this electron pair as a nucleophile, and push those electron pair from the backside. That's, in my opinion, is only partially true, fundamentally wrong. And we should think that it is an electron deficiency that bring about some chemical processes which is lacking perhaps here in an effective way. And if you compare this process and this process, this is a borane. Then this is the mechanism of Brown's hydroboration. This is a 6-electron species, and isoelectronic with this carbonium cation, carbocation. No wonder this reaction proceeds so well. Even at 0 degrees, even at minus 78 degrees, this reaction can proceed. Okay, and if this reaction is so facile because of the availability, presence, or action of this empty orbital here, what about this species? Now we have replaced the boron with a this zirconium group, but in this chlorohydrido zirconosine, sometimes called the Schwartz reagent, but that doesn't do justice to the discoverer in Australia. So anyway, this reaction proceeds very well, very fast. No wonder, because if you focus your attention on here, empty orbital and then a sigma orbital, empty orbital and a sigma orbital, they proceed in the same way. So that's interesting. And what's wrong with this Grignard chemistry, uncatalyzed? I didn't think much about it until recently. And then I thought maybe there's something wrong with this acid base coming together and form a salt. Even if thermodynamically this is an overall downhill process, there is something wrong. What is it? Well, usually I give 5 to 10 seconds, but today I will go ahead and tell you. Well, as these acid and base come and B begins to transfer this pair of electrons to A, base, transferring pair of electrons to acid. Then naturally, this species, assuming that both are neutral, doesn't matter what level you consider, then it will be positively charged, begins to become positively charged. As A begins to receive a pair of electrons, naturally it will be negatively charged. What do these partial charges will do to electrons? Well, B began donating this pair of electrons by virtue of this polarization, the partial positive charge. A split second later, it says, come back. This positive charge will attract negative electrons, as you know. A, let's say neutral one, as it begins to accept pair of electrons, it will be negatively charged. This negative charge will start repelling back. This 2 electrons. Go back. I don't want. And this will raise activation energy. Of course, any reaction tends to have activation energy, but so this is what happens at one energy level. On the other hand, the solution can be provided by using d-block transition levels, as Fukui, using his frontier orbital theory, presented this, and Dewar presented this synergistic, so-called synergistic bonding scheme, 1951. Fukui presented his frontier orbital theory right after World War II, 1940 something. And a little later, 1965 or so, beginning with 1965, Woodward and Hoffman provided further detailed this orbital symmetry matchup aspect. What this means is this. So this empty orbital interact with the pi orbital begins to accept 2 electrons. That alone, as I said, will raise the activation energy. But as I was telling you, d-block transition metals can have filled-nonbonding orbital. So these are filled-nonbonding orbital. They can back donate 2 electrons into what we call a pi star orbital, empty orbital of double bond. So inside here, 2 electrons are to shift from bottom to up in this direction. That generate polarization. But outside, 2 electrons are to shift from top to down, once again generating this polarization. But the directions are opposite. This is a two-way deal. So overall, the overall polarization is minimal. This will significantly lower the transition, this energy of activation. And you can see that, and I think this is one of the single most important findings, synergistic bonding, in this organometallic chemistry. And our community, OMCOS, has adopted this thing just as presented by Dewar as our society community's logo. And I frame it in my office, at my home. I pray sometimes. But I am thinking of this thing all the time. And this has led me to discover some reactions, as I will tell you. So if you think of this alkyl iodide here, alkyl, sp3 hybridized, alkenyl iodide, the Grignard reagent will probably attack here, or more likely attacks here and then eliminate without forming a Grignard reagent, coupling. But palladium, because of this, palladium can interact with a pi bond much more readily than the sigma bond. And then it will react. So we estimated the reactivity ratio here and here, 1,000 to 1. So we don't see any reaction here. We see reaction here. So formation of this cross coupling. Okay, but I think I will have to come back to this one and to wind up my talk today. If you believe in this, which I do, we should believe in what I show here, here, and here. This is my recent past, present, and the future research foundation. So what is this? Well, here, if you just consider this part, okay, then that is reproduced exactly in the same way. Well, sorry, I don't show negative empty lobe here and here, but forget about that. So this one, and this one, oops, come on. This one, exactly the same. What I have done is to replace this dehybridized filled non-bonding orbital, two electrons. This one with hydrogen metal sigma orbital, two electron. Or carbon metal, two electron orbital, two electron. Or heteroatom metal, two electron orbital. Metal, two electron orbital. What else do you have in the periodic table? That's our territory, ballpark. Nothing else. I'm showing everything here, here, and here. In all cases, with all elements, we can have this, or this, instead of these two, this one. And then we can have synergistic bonding, this way. Synergistic bonding, just like this synergistic bonding. This one just forms a complexation. But in these cases, there are more interesting consequences. That consequence is that in this way, the consequences are hydrogen attached here and the metal attached to hydrometallation. In this case, carbon may attach to this carbon, and metal may be attached to this carbon. Carbometallation. Here, heteroatom and the metal adding to double bond or triple bond, for that matter. And the metal bond attaching. Just a tremendously wide scope, range of various kinds of reactions can be written, their mechanism, even before you discover, or some have been discovered like this. But that's my essence of the maybe second part. So I'm going to have to skip this one. And here it's getting to be a little too much. So, and well, here's going back to that cross coupling. We have made a major discoveries in 1976. And here I'm showing nickel or palladium-catalyzed alkynyl aluminum cross-coupling. And notice the level of selectivity, and yield. But turned out we were disappointed when we shifted to not alkynyl aryl cross-coupling, arylated alkene, when we shifted to alkynyl cross-coupling. With nickel, selectivity for EE isomer formation went down from greater than 99% to 95%. When we tried EZ diene formation, it went down further to 90%. That's the time, 1976, I said, well, we better look for better element than nickel. It still has to be D-block transition metals. We screened, naturally, nickel, palladium, and platinum. The Mendeleev already told us 50 years ago or so what we should do. So we screened. Platinum reactions were too slow. And when we shifted to palladium, yields are similar, but we were able to maintain this 99+% selectivity in all cases. That's the time when I said, it's got to be palladium. That was in 1976, and everybody else sort of followed suit, in my opinion. And that was a big moment for us. And then we said, if palladium is a major player, probably what we put here as metal, sometimes we put aluminum, sometimes zinc, and so on, probably doesn't matter so much as long as this thing can transfer the group attached to metal to palladium. That was our notion. And in fact, we did that in 77, but we ended up publishing in 78. We screened about 10 metals, put here. Out came zinc, which we already knew was probably the best. Fast reaction at room temperature, short time, 90-ish% yield, and which later was tagged as Negishi coupling. We also did this borate thing. Reaction was a little slower. We needed to reflux, but yield were comparable. That became Suzuki coupling. And we also had the tin one. Reaction was a little slower, but it was probably the second best. Still a coupling. So this way, you can discover many reactions, but these namings, I don't know how to. Anyway, as I was telling you, with the palladium as a catalyst, in these 5 different kinds of reactions, as long as you use a chelating ligand. The chelating, even before you try, chelating ligands they have to be better, because when metal, palladium, goes in here or here, if one comes off, then that should snap right back in the original position with very, very high probability. So we figured that the chelating ligand should last longer, and it turned out to be so. I don't show everything, but in all these cases, we reached a million level while maintaining at least a 60% yield level. But since then, we said nothing below 70% is acceptable. So, but anyway, the reaction is very highly catalytic. And so this turned out to be one of the most, I'm running out of time. So one of the most widely applicable CC bond formation. And this is a compound historically synthesized just once by K.C. Nicolau. I don't want to count the number of steps. Well over 50 steps total, linear steps total. But some years ago, we began demonstrating just this part. It's not even half, but these are our specialties. And without spending much time, we got this thing in 40% in longest linear steps in 5 steps. And I want you to note that we never generate any isomer anywhere. I mean, stereo, isomer. That's the level of selectivity. Here we use aluminum, zinc, of course. Coupling is always done with the palladium, and as you can now tell, chelating one. Here's some academic 5% more sneaking in. That's not good. Anyway, so I just want you to note, and this is the one. This compound had been synthesized before us, spending some 10, 15, 20 steps. But from a commercial, everybody uses start from this one. Commercially available one, we were able to put together in 4 steps in high, reasonable yield. But here, probably no big deal, except that here is a Brown's crotal boration, a very useful reaction. Once we got this one, in this case, we put together by going through the Heck reaction and HWE reaction. We're not using Negishi coupling. So what my message here is that when we should use the best reaction in a given situation, and at times, I think we believe that our kind, Negishi, Suzuki kind of cross-coupling, reactions of widest scope and then generally the highest selectivity, but not always the best. So here is an example where Heck reaction is good only because we get this unfunctionalized terminal alkene. So if we are to halogenate here, it will cost 2 more steps, which we avoided this one. And then this one and this one, HWE kind of alkene regions are not always highly selective, but when it is conjugated like this and conjugated like this, they work very well. Anyway, I have to hurry up. So this one is a mycolactone B synthesis, and if you look at any place, here, we really mean it. We just don't generate isomer. This is the beauty of a Lego game. In other words, you synthesize Lego game piece A as a pure material, and Lego game piece B as a pure material, and hook them up under all kinds of cross-coupling conditions. Nothing is messed up. So high stereo selectivity, regio, and also regio, I want you to note that in our cross-coupling, we have regio marker here or regio marker here. So regio chemistry is not also messed up. Yeah. And so I want to wind up my talk by showing recent synthesis of 8 possible, 2 times 2 times 8 possible stereo isomers of trienoate. 1, 2, 3, 4, and then 4 more coming up. In each case, in all cases, stereo selectivity. Honest to God, we don't see any stereo isomer. And we have, if this is present, we know where this appears. There's none. Or likewise here. So this is a very clean, highly selective synthesis. And yields are okay. And 2 more. Actually, 2 out of 4 more. This one, this one. These become somewhat more challenging, but still 88, 98 plus, high yield. And finally, these 2 most challenging. They have never been synthesized before, except as a minor byproduct obtained in 4 or 5% yield. But as you can see by this Lego game approach, by forming this one, and that will guarantee that this is Z. And then I think we have here, we made this piece. Oops! This is, I'm too honest. Here, did we detect 3% of the other isomer? I'm sorry. I was off by 1%. But this is the only time when we observe less than 98. Anyway, so using these, we hook them up. We purify this one. Yeah, after purification. Okay. So we can synthesize all 8 isomers. And I think this is about time for me to wind up. I'm sure you got the key message here. And of course, as I showed you, we can now come up with various kinds of not only hydrometallation, but carbometallation. And here we are reporting this kind of carbometallation. Simple alkene of 1-point binding. Sharpless, Noyori, oxidation, reduction. For satisfactory results, you need allylic derivatives. Those are substrate of 2-point bindings. Double bond and OH, allylic OH. In this, our carbometallation, here going this one, from here to here, we don't need any other functional group. So these are called the substrate of 1-point binding. Using this zirconium and aluminum reagent, we put methyl here and aluminum here. Okay, so let me just yeah. Okay. So I promise this is the last slide. Okay. So this compound is called the acid component of pring gland wax of gray lag goose answer. So apparently this part of geese goose, there is this compound serving as a super grease, I guess, when they fly from Siberia to Japan, Hokkaido. Kenji Mori came up with a wonderful synthesis, but that required 20 steps, not 10. Obtained this one in overall 1% yield. We got this in 12% yield. These numbers make approach being even practical, I believe. Okay, so we start with allyl alcohol, $1 per mole, and we add methyl and aluminum, as I told you. Methyl and aluminum. OH is extra. We don't need OH. So methyl, aluminum was iodinated in situ, and then this was protected in situ In one step, we get this thing from here in 80+% yield and in 80+% EE. I think it was 82. But anyway, one step, and then now cross-coupling is waiting here, vinylation. In two steps, we get this one. These are very, very useful intermediate. Now comes the fun time. Allocate maybe 2 weeks, 10 days, 2 weeks. What you do is ZACA, ZACA, ZACA. 3 steps. After first 2, you do a vinylation to elongate. The third one, you oxidize to get this alcohol. This is a real fun reaction. And then you go from here to here in 3 short steps. This one. What you have is obtained in about 30% yield from here. 9 to 1 to 1 to 1 to 1 mixture. What is 9? 9 is 9 you see here. 9 is what you want. 1 to 1 to 1 to 1. That is out of 16 possible isomers, there are 4. Those are single site epimer. 1 site wrong, 3 sites correct. Okay? Those are seen like so. So it's not pure. But we've learned that as long as you have a yellow box, that is a 1, 2, 3, 4. 2,4-dimethyl 1-hydroxybutyl. That's what we call a yellow box. You tend to get those in this business very frequently. Then you can, pretty much regardless of what you have here, you can purify by simple chromatography. Usually 1 round is enough. So you put it through chromatography, then you purify this yellow box. Outside the yellow box, a slight change, but not much happens. But go ahead and convert this into methyl, as shown here. In this case, there's nothing like a copper-catalyzed Cauchy-type alkylation, which proceeds very well reliably. Then you can deprotect this one. Out comes this 2,4-dimethyl 1-hydroxybutyl yellow box. That corresponds to the other half. Put it through column chromatography once, then you have pure one. And then after 2 oxidation, you get this one, this way. And you can tell that what we have here is very highly pure, and you believe in this statistical amplification business, which nature has exploited for billions of years. You don't see in your amino acids even trace of D and so on. And here we estimate the enantiomeric excess to be 99.99%. And here you can sense that. So if this were racemic, the mixture, you see a huge signal in the middle, which I'm not showing. But this region is dead flat. And our calculated estimation is 99.99% EE at this point. So that's what we are pursuing right now, and it's been working very well for us. And only when we only have one chiral center, then the best thing still is lipase-catalyzed acetylation. So compound like this used to be a very difficult one to synthesize. This one is touted as being effective against Alzheimer's disease, arundic acid. So here there's a chiral center. This one is a normal propyl chain. This one is a normal hexyl chain. These groups are very difficult to distinguish. But our strategy is shown here. We get this thing, we get this compound, the same, but this one is 82% EE here. But because there's iodine, which has a selectivity value, E value of about 33, so these two groups can be readily distinguished by lipase-catalyzed acetylation. Then you can readily improve, well, we like to maintain higher yield, but from 82% EE to 99% EE, or even higher if you want it. But we have demonstrated it is readily purifiable. After purification, now you do a cross-coupling. In this case, again, alkyl-alkyl coupling. So there's nothing like a copper-catalyzed Grignard cross-coupling. And then we get a pure one, which are otherwise very difficult to synthesize as a pure species, as you can imagine. Okay, so over the years, for the discovery and development of palladium nickel catalyzed cross-coupling, I'm very sorry that I've gone over time. More than 100 people have participated in this. But I always remember the first quintet. Dr. Baba, Tony King, Dr. Okado, Kobayashi, and David Van Horn. And of course, I thank them all. On the chemistry that I only briefly touched on last, David Van Horn, graduate student, first discovered the triple bonded version. And there was a 17 long year gap. We needed to wait until Denis Kondakov, coming from St. Petersburg, discovered what we call a ZACA reaction. And a more recent group, and some of our funding agencies. And thank you very much for your kind attention. Thank you.